All right, my friends, let's take a look for part A. I personally think of this as the integral from 1 to infinity of 1 over x dx. And then to graph it, I would just graph the function that is in the integrand. So f of x equals 1 over x, starting at 1. I'm going to use kind of a non-square scale here. Okay, so let's see, put 1 in, you get 1 out. Put 2 in, you get 1/2 out. Put 3 in, you get a third. Put 4 in, you get a fourth. Put 5 in, you get a, etc. Okay, so here is the graph. Let's see. Okay, and because one of the bounds is infinity, it would theoretically go forever in that direction. Anyway, and then the bounded region, or I shouldn't say bounded region. It's not very bounded, is it? Anyway, the region, that we would be essentially finding the area of would be this region right here. And really what makes this integral improper in this case would be that, one of the bounds is infinity or is infinite in nature. And it causes there to be, in a way, kind of this unbounded piece to the region. And so if I was to ask you, what would you say the area of this region is? I get all sorts of fun answers. One very common answer would be that this would be an infinite area, um, and we'll find that's correct. That the fact that this region is unbounded here, and for this problem does cause the value of this integral to be infinity, and we'll talk about the details as to how to get that soon. All right, now let's take a look at part B. So this time we'd be looking at the graph of f of x equals e to the negative x. So if we put 0 in, we would get 1 out. And then if we were to put 1 in, we'd be getting like a third out or so. I'm just grossly treating e as if it's a 3. I know e would be so offended if it was here. Anyway, let's put 2 in, we'd get grossly 1/9 out. Put 3 in, we get grossly 1/27 out, etc. What would be next? 1 over 81. Okay, it's hard for me to draw this one to show that we're not actually going to get a value of 0 out, but you can see we do get incredibly close to 0 very quickly on this one. And then I'm shading in the area this integral would be evaluating. There we go. Anyway, and then, this integral is improper as well, right? I think your upper bound is infinity, and so, but if somebody says, "Quick, guess what the area of this region is," a lot of folks would guess infinity as well, along with part A. But we're going to find and show in this lesson that while the answer to part A is the value of the integral is infinity, we will actually show that you get a finite answer for part B. So. And then let's talk about how come. In the previous lesson, we, in section 7.7 with L'Hopital's rule, we talked about if inside a limit you have something approaching infinity times something approaching 0, that this is an indeterminate form, that you could get all sorts of fun things out of this, right? Like you could get infinity if this value gets to infinity before the second value gets to 0, then maybe this result would approach infinity. Or you could get 0 if this number gets to 0 before this number gets to infinity. Then you could get 0, for your answer, or anything in between, depending on the rates at which the first function rule is approaching infinity and the second function rule is approaching zero. The reason I'm mentioning this right now is because remember that the idea of area, of finding area, was that you're adding up infinitely many, infinitely thin rectangles, right? Oh boy, my choices for how to do the pen is interesting. But anyway, so you're adding up infinitely many. So we're adding up infinitely many rectangles. But then the heights or areas of these rectangles are approaching zero. And so at the tail end, right? And so it's just a matter of like, do the heights approach zero fast enough for you to get an actual finite answer or not? And so the answer for part A is that your little heights for this function do not approach zero fast enough for you to get a finite answer. But for part B, you can see that the values are approaching zero faster than the values were in part A. And as a matter of fact, we'll show that the little heights of your rectangles or areas of your rectangles were approaching zero fast enough that even though you had infinitely many of them, you can still get a finite result by multiplying those two together. So there you go. All right, so that's the idea behind this lesson. And now the rest of the lesson is all about kind of just the moves of how to do it and getting the practice in. So let's start example 2. We're just going to recycle from example 1, and we're just going to show how to do the algebra behind getting the answers. So I'll do part A with you, and then I'll butt out and let you do part B. So for improper integrals, the first thing that we do is we change the notation. So what's so improper about this integral in the first place? And we would say it's the upper bound. And so you'll actually change that the notation. So we're going to say the limit, and I tend to use b for upper bounds anyway. So the limit as b approaches infinity of the integral from 1 to b. And then I'm also going to change the way that integrand looks. I personally like it a little bit better when it says 1 over x dx. You could leave it as dx over x if you like that better. Okay, so that's the first thing you're going to do is change the notation out. You're going to swap out anything that's improper in your bounds with this little limit notation, okay? Then the next thing you do is you just follow your nose and you work from the inside out. So the next thing we're going to do is the antiderivative of 1 over x. So you're going to carry the limit as b approaches infinity down, and then you'll take the antiderivative. You'll get the natural log of the absolute value of x, and then we're going from 1 to b. Okay, keep following your calculus nose. Leave this limit off until the very last. And then you'd have the limit as b approaches infinity of the natural log of the absolute value of your upper bound minus the natural log of the absolute value of your lower bound. Okay, evaluate what you can. The natural log of 1, it's asking e to what power equals 1, and so the answer is 0. So really, and you could take an extra step to write this or not, but really you're just left with the limit as b approaches infinity of the natural log of the absolute value of b. Okay, well, now let's go ahead and see what happens if you let b approach infinity. So natural log of the absolute value of infinity. This is if you could just think about the natural log graph. And so what happens as your input approaches infinity, your output would also approach infinity. There we go. Okay, so my friends, this is the algebra work that it would take to show, oopsie, that the area of this unbounded region actually, is infinite. So we'll say infinity units squared. There we go. Okay, so now go ahead and see between now and the next video, see if you can do similar work on part B and show that you actually do get a finite value for the area of the region as described in part B above. See how it goes. Good luck.